Okay. Uh, Let us wait for a minute, then we can start. Okay, till now, no one has joined. So let me start. All it's audible. Mhm. Let me share my screen. Is it visible?
Yes,
Oh, okay. So, do you have any doubt from the assignment questions or the lectures regarding last class regarding the lectures, last week lectures?
week 5.
Week 5 or week 4? Anyone? Week 6 I can't answer, but week 4 or 5 I can answer.
Currently, no problem.
Okay. So let us start. When we try to just open the questions for the previous materials. This is week 5 and question number 1.
Will you do the Helmholtz equation part?
Helmholtz equation or Helmholtz free energy?
Yes, that's only in this lecture.
But that is not taught in the lectures, lectures uploaded in this week. I can do, that is not a big deal. I can do, it's easy. If you want, I can solve.
A equals to U minus TS. This week, I think it
Yes,
has been
that's,
taught.
yes, that is taught, and the form, okay, I will do. It's not difficult. And Gibbs free energy, Helmholtz free energy, both I will do.
Okay, so please, it will be very great if you can do.
Yes, I will do, but at the last, I will do it. Okay. First, let us solve some question,
Okay,
then
okay.
I will do that. Okay. The first question is, the molecular partition function for system is given by Q. This is a molecular partition function. Okay. A t to the power 4, where A is a constant. Okay. Now calculate the internal energy, heat capacity, constant volume, and entropy, considering first molecules are distinguishable, and second molecules are indistinguishable. And also calculate the indistinguishability factor for each thermodynamic quantities. Is the question is clear?
Yes.
Okay. So in last class I discussed, and also the also Sad discussed that Q is a canonical partition function, which is function of n, v, and t. This canonical partition function essentially we know that it can be written as q to the power n. Okay, where q is the molecular partition function. This is our molecular partition function, and this is our canonical partition function. Okay, so this is clear, but this equation is valid for this entire formula is valid for
Distinguishable.
distinguishable and non-interacting particles. Okay. Now, if the particles are interacting, then we have to only consider the Q. When particles are interacting, you can't express the partition function, canonical partition function in terms of molecular partition function. That is very, very difficult. That is not possible. But when particle are indistinguishable, then you can do something like, let's say, then it will be Q is equal to, not Q, Q n Vt. It's better to continue the variable. Then it will be Q to the power n by n factorial. Okay. Uh, but one thing you have to keep in mind that this formula, this is for indistinguishable particle, it's correct. But what type of particle? It's not generalized formula. It's not always true. because if you look the assumption, okay, one thing also you can write this small q. Okay, what will be the variables v and t? It should be, because q is function of nvt and you have taken care that n here, so obviously the small q should be a variable of v and t. You know this thing, right?
Yes,
And if I ask how this q is a function of v and t, how you can answer this? Why this molecular partition function is a function of volume and temperature?
because it is in the expression of partition function.
So what? Partition function you know, but that is a general expression, right? E to the power beta epsilon j, where the volume and temperature is coming. Okay, temperature I can consider is v beta 1 by kBT, but volume, how the volume is coming? That I have already said in one lecture, I think. Because you know that for molecular partition function, the total partition function will be Q translational into Q vibrational into Q rotational into Q electronic, Q nuclear, all, right? All, till now we have only studied that this Q translational. This we have studied. This we will study in the upcoming lectures. Okay, but you know the what is the form of Q translational? Q translational is V by lambda cube, right?
Lambda cube.
So this is a function of V. And if you look at the other express other partition function, that qv already we have studied, not formally, but we have studied that for harmonic oscillator, that the partition function for harmonic oscillator is essentially the qv. What was that? 1 by 1 minus e to the power minus h nu by kBt, like this. If you don't consider the 0 point energy, and if you consider the 0 point energy, then probably it will be 2 h nu by kBt, or 2 kBt may be there, something like that. But look at here, only t is there. So explicitly, if you want to write, then this is a this first qt is function of v and t, and other are function of only temperature. Okay, so the translational partition function is only depends on the volume, but that's why this overall partition function will depends on volume and temperature both. So this is our,
Translational partition function not depend on temperature.
yes, depends on temperature. That's why I've written v and t both, because temperature dependence will
Okay.
always be there, because if you look at the general form of the partition function, there is temperature, right? Beta. So how you can ignore the temperature will always be there. This
Which
whatever,
temperature? The beta or in the lambda cube?
in both cases there is a temperature. Beta is also temperature 1 by kBt, right? Beta is temperature.
Yes.
What is the form of the lambda? It is h by root over 2 pi
2 pi
k
mkbt.
kBt. So you can write in terms of beta as well. That does not matter. Beta is 1 by kBt. So essentially beta, what does it mean? Inverse temperature. It has a name, right? I have also inverse temperature. So that's why the Q translational is function of both volume and temperature. And that is the reason of I said that Qt is an extensive property. But other partition function are not extensive property. They all are intensive property. But Q translation is an extensive property. Uh,
Because it depend on external temperature and volume.
No, it depends on volume. What was the definition for extensive properties? Which depends on the volume. Okay,
Depends on the quantity.
quantity means volume or mass. That is called extensive property in thermodynamics, like our any internal energy, or internal energy is extensive means if you double the volume or double the mass, the internal energy will be doubled. The enthalpy, entropy, all the state functions, all state functions are basically the extensive property. And intensive properties are like temperature. Temperature is an intensive property. Uh, or mu, chemical
Density.
potential, density, these are all intensive property. But density and chemical potential, these two are intensive property. But why these are intensive property? Because mu is a ratio of two extensive property. Density is also ratio of two extensive property. That's why these are intensive. But temperature is not a ratio of two extensive property, but still it's a intensive property. Okay. So temperature is very special.
Okay.
Okay. One more thing I want to say.
What about pressure?
You you think that what is the pressure? Pressure will depend. Okay. Just write down the equation PV is equal to N at T. Now P will N at T by V. What is T? T is intensive
Intensity.
property. N is extensive, V is extensive. Now N, V both are extensive. The ratio will be intensive.
Intensive.
Yes. So pressure will not be that. Now if you double the volume, you can think like that. You are doubling the volume. Temperature is fixed. Then pressure will change or not.
Change.
Pressure will change. So it depends on the process, which process you are taking. Now, if you take a isobaric process, then pressure will not change. Okay. So that's why pressure one. So that's why you have to consider the process for pressure. But mass, volume, temperature, these are very straightforward.
Okay.
This is what I want to say. I forgot 1 minute. Okay. So this formula q to the power n by n factorial, this is for indistinguishable. But what is the type of particle we are considering here? That is not mentioned clearly. So that's why I'm saying it's very important to make clear that all are the Maxwell-Boltzmann particle. Here also, it's very important. We are considering the Maxwell-Boltzmann particle. Maxwell-Boltzmann particle are, I said in the first class that classical particle are,
Indistinguishable.
no, Maxwell-Boltzmann particle are distinguishable. Classical particle, right?
Yes. Yes. Classical particle.
So particles are two types. One is our classical particle, and another one is quantum mechanical particle. So classical particles are always distinguishable due to its trajectory. I said that it's always distinguishable, and this type of particle, this type of classical particles are basically follows the Maxwell-Boltzmann statistics. That's why it's also called Maxwell-Boltzmann particle. Okay. For that particles, you can write Q is equal to Q to the power n. Now coming to that, the quantum mechanical particle. There are two types of quantum mechanical particle, fermion and boson. Fermions and bosons. Okay, for fermion, they followed the Fermi-Dirac statistics, FD, and boson, Bose-Einstein statistics. These are known. But here, if you consider, that is an assumption, if you consider the classical particles are indistinguishable, okay, again I am repeating, you imposing the condition that classical particles are indistinguishable. So you are taking particles which are indistinguishable, and you are also considering the Maxwell-Boltzmann statistics. Then only under that consideration, if you consider these particles are indistinguishable, then only you can write Q is equal to Q to the power n by n factorial. But for quantum mechanical particle, bosons and fermions, you can't relate the canonical partition function and the molecular partition function, capital Q and the small q, because they are interacting particle. Because in boson, you know that in one state there are more than one particle, in fermion there will be only one particle. So it's very, very difficult to It's not difficult, it's impossible to relate q and small q, capital Q and small q. So how you can now argue that when you are taking a molecule, a set of molecule, let's say Avogadro number of molecules are there, and in class you have said that when these are all, let's say, same type of molecule, helium gas, then all molecules are indistinguishable, right? These are in, these molecules are classical particle, but still they can be considered as indistinguishable.
Yes,
This may be contradictory because I said reverse thing first, that classical particles are always distinguishable, yes. But in case of helium gas or this type of similar kind of gas, what happens? There is a n number of molecules, and uh, all molecules are not fixed. They are moving. They are gas. So in that condition, you can't keep the trajectory. Fine. Okay. What I have said, that why these are distinguishable, because all classical particle has a perfect fixed trajectory, and following that trajectory you can identify the classical particle. But when there is a n number of molecules, n number of huge number of gas, and all gas are moving very fast, you know the velocity for the gas molecules, that is very fast. In that condition only, then you can't distinguish those molecules. Let's say you have 10 balls and that balls are moving, all are identical, then you can track them. Always you can track them. But when these 10 balls become thousand of balls and all balls are moving very, very fast, then you can't track them. Na? In that condition, you can consider, though it's an approximation, you can consider that molecules as indistinguishable molecules. Okay, and you have to consider that, then only you have to apply this formula q to the power n by n factorial. So these are all for Maxwell-Boltzmann statistics, not for the quantum mechanical particles, because molecules are not quantum mechanical particles. Okay, when you have,
can I ask one doubt?
yes,
Why carbon monoxide solid is considered as distinguishable?
solid, that they are not gas, so they are not
Yes,
moving.
but there is thousands of molecule.
Yes, but they are not moving. What I have said, that you trajectory must be there. So you can track when they are not moving, then easily you can distinguish. Na? Let's say you have 1,000 ball. So you can distinguish, they are not moving. So A, B, C, D, 1, 2, 3, 4, you mark them. You gave a sticker to each and every ball. So there are 1,000 balls. So easily you can distinguish
Yes, yes.
that, like that. When they are moving, then the difficulty arises, right? When they're not moving, then it's very easy. You can think in terms of coordinate.
If there is small number of molecule, then I can take it indistinguishable or distinguishable.
Always it will be distinguishable. If they are not gas, they are solid. Always that particles are distinguishable. You can
No, that is
distinguish.
gas. Small number of molecules, 5 or 10 molecules of gas, moving in very high speed.
Okay, five. No, in that case, you can distinguish that. You can distinguish. You can
Okay.
think like that. When the n is very, very small, then ultimately this n factorial will be very, very small, and that factor will not be alter the result very much. But it's better to consider this when the molecules are gas molecules, and you can't. Let's say you have 5 molecules, right? And let's say for argument, you can take 5 molecules, but using 5 molecules, what property will measure? Internal energy, or because you have to keep in mind that all these properties are average, and using 5 or 6 molecules, you can't take the average. For taking average, you have to consider at least 1 mole of that sample. So
Yes.
for that, you have to consider this distinguishability factor, and you have to calculate this q to the power n
For
by n
1 mole,
factorial.
it's indistinguishable.
Yes, in case of 1 mole, if they are same gas, molecule, then. But if you mix two gas molecules, let's say helium gas plus neon gas, then they are not indistinguishable molecules. They are distinguishable, and there are two groups now. There are two groups now. You have to now account that two groups. If it is n1, if it is n2, then it will be q to the power n1 by n1 factorial, q to the power n2 by n2 factorial, like this. Okay.
It is additive or multiplicative
What should it be?
between these two, q to the power n1 by n1
Hmm.
factorial and q to the power n2 by n2 factorial.
You guess
Which
what should
sign?
it be? It should be
Plus.
no, no, multiplicative. Partition function, no? Here also you
Yes,
do.
but multiplicative in nature.
But these are not very uh, perfect answer. Okay, these are all approximated. That you have to keep in mind. This may give a correct analog to the classical thermodynamics, but these answers are not very perfect. The derivations are not very perfect. Now, in case of boson, under some restriction, I'm not going to discuss that. Under some restriction, not for all cases, for some cases, you can consider this. For some cases, okay, but it's not general. For some cases, for boson, you can consider, but for fermion, it's very, very difficult. Very, very difficult to derive such an expression. Okay, so what was our question now? Yes, this is Q. Now we have to small q is given. Now we have to calculate the internal energy, the heat capacity, and the entropy under considering the distinguishable and indistinguishable both. Okay. So first, let us consider molecular distinguishable. Distinguishable. So now what will be the q is given, that is a into t to the power 4. So and then what will be the capital Q? Capital number of molecule is given.
Q to the power n by n factorial.
No, Q to the power n only. Okay, for n number of molecules. Let us.
Indistinguishable. Oh, sorry,
No,
distinguishable.
these are distinguishable. We are considering. Okay, these are for 1 mole. Okay, this I forgot to write for 1 mole. Each and everything for 1 mole. So what will be now capital Q? Q to the power
N
n.
means 1.
No, no. This is capital N, number of molecules, not one. Na is 6.023 10 to the power 23.
Okay.
This is not small n, not number of mole, number of molecules. Okay. So now what will be our internal energy? You know, capital E average, that is Kb T square, then dlnq dt at constant volume, if I'm not wrong. Yes. You can calculate in both ways. This is direct from canonical ensemble, or you can calculate this small e. Last class I have discussed, which is kbt square dlnq. This is not actually d. It should write del because partial difference. dlnq del t constant v. Then you can also multiply it with cap na, and you can calculate this e. Both are correct. Both will give the same result. So now here if you put it, then it will be kbt square ln q. What will be ln q? Na ln
A into
small
k to
q.
the power 4.
So Na will be there. It will be del t of ln small q at constant volume, right? And what is the small q? A into t to the
A
power
into
4.
t to the power.
A into t to the power 4. So A, okay, let me write. A into t to the power 4. So ln q equals to ln A into t to the power 4 means ln A plus
Plus
4
ln t to
ln
the
q.
power 4.
Okay. So it's clear
First
that
one is constant.
it will be 0. When you take the derivative, it
Yes.
will be 0. It's constant. So only that 4 ln q will be there. So let me bring the 4.
Yes.
This is at constant volume. So what would it be? kbt square Na, it is 1 by
by T.
2. So it should be 4
Del
Na kb
T
T.
only.
Okay. So 4 Na kbt. Or you can write it 4 RT.
Na beta.
Na beta no, Na by beta. But that is not
Yes, sorry.
required. We have to always express in terms of our classical variables, right? Means our thermodynamic
Classical.
classical thermodynamics variable. Means I want to say not the uh, chemical thermodynamics, better it's say, like entropy, temperature, R, pressure, volume. These can be measurable quantities. Pressure, volume, not
Yes,
entropy, R, V, T, like this. We know that this R is always Na into kb.
yes.
So that's why I written is 4 active. Okay.
Always we should return in this form.
Yes, it's better. If it is not 1 mole, let's say if it is not 1 mole, then what should it, the answer will be? If it is not 1 mole, then it will be
For
4
inactive.
n kbt. N is not Na. Then how we can write it? Let's say n is the number of molecule you don't know. Then how we can write it? It's easy. Just put instead of kb r by na t, and then you can write it for n by na or for n by na rt. That means for small n rt, because capital N by na should be the number of mole.
Yes,
So it's a correct answer, but it's better to write in this form. Okay, because you don't know the number of molecules, so better you know the number of moles. These are the uh,
yes,
chemical thermodynamical property I want to say. This Kb, capital N, this number of molecules, Boltzmann constant, these are actually the statistical properties. Okay, so that's why I think. So it's 4RT, but this is considering the indistinguishable. So now if you calculate that, considering the, sorry, these are distinguishable. First, let me write, not heading should be internal energy. Then internal energy. Now considering the distinguishable, we did this. These are considering distinguishable. Now if the molecules are indistinguishable, then what will be the changes?
there will be n factorial divided in this.
Yes, so you can direct do it. Okay, let me do it. Now Q will be Q to the power n divided by n factorial. But we need ln Q, means ln Q to the power n minus ln n factorial. So now it is n ln Q, and it is not n Na, because we have already considered. Let me write n, but here n is equal to Na, because we have already considered 1 mole, and it will be n ln n minus n using the Stirling approximation. Okay, I think it's clear. So it ln Q. Hence, what was our internal energy? kbt square d ln Q dt at volume. So we can also simplify this ln a t to the power 4 minus n ln n minus n.
This is constant.
Which one is constant?
N ln n minus n.
In terms of temperature, it will be constant, because there is no temperature. That's why it will be okay. Let me do it. So what will be dln q dt? Only the first term will contribute. So it will be n 4 d
By T.
ln t by t. Is it clear? or I should
Yes,
do the intermediate. Okay. So it is
no
4n by
problem.
t. So kbt square, it is 4na by, so it is again 4n. So indistinguishability factor, what will be the indistinguishability factor? Let me I termed as I. For internal energy, it will be internal energy considering indistinguishable particle divided by considering distinguishable particle. So in both cases, these are 4 at P, 4 at T, so it will be 1. Is it clear?
Yes, but why there is no difference in distinguishable and
Yes.
distinguishable?
Why there is no difference? Because you are considering, this is due to the expression of our uh, Q, small q. You look at the small q only depends on temperature.
Yes,
Okay. Now, you are again you are considering the internal energy, and in case of internal energy, that is a derivative with respect to temperature only. So when you adding the n factorial part, that will not contribute anymore.
yes, yes,
That's why. Because now if you think in terms of physical picture, then also you can think why the n factorial came. N factorial came because there are n factorial arrangements are there. Due to overcounting, you have to divide it by n factorial.
yes.
That's why it came, huh? But that overcounting, in case of indistinguishability, that overcounting will not contribute in case in calculating the internal energy. That's why it does not matter. That overcounting is there, obviously. That's why you have to divide it by n factorial. That is correct. But due to, if you don't consider that n factorial also, that overcounting will not change the result. Because
So
they,
every property will be same.
let us check whether every property will be same or not. What do you think?
Then internal energy will also be same as this.
Internal is same. Now, if you consider the uh,
Entropy will be.
heat capacity first, CV. What is the formula of CV?
Classical.
CV is always same.
Del U del T at constant V.
Let me put in the chart. So it is del U. Del U means del E average divided by del T,
At constant volume.
a constant volume. Now, if the del E is same for both cases, obviously CV will be same for both cases. This is very much straightforward.
Yes.
Okay. So it will be 4 RT for both cases. So it is 4R. So I'm not doing the heat capacity part. And now what do you think for entropy?
It should also be same.
It should. Why that indistinguishability part, number of arrangement part,
No, no,
that
it's different.
did not contribute in case of internal energy, but in case of entropy, the randomness will increase definitely. So it should contribute.
Yes, it will definitely contribute.
Yes. So now you can do. What is the formula for entropy?
KB ln Q
Kb ln Q, considering the 0 point energy. If you don't consider the 0 point energy, then that U minus U0, that part should also be there. In the class, side did considering that, na? So here also,
yes,
so let me
U minus U0 by T.
U minus U0 by T. But if you don't consider the, if you consider the 0 point energy, then U0 will not be there. U by T will be there. So let me do it formally.
Yes,
Okay. Let me calculate the S. Okay. Internal energy, you know. What is the internal energy? That is our
for RT.
kV. No, no. The original expression. This is original expression. What the main expression was? This. In this was the original expression. There are three expressions, right? If you remember, in last class I did. When you put 1 by kBT instead of that beta, you will obtain this, right?
Yes.
Okay. So now the entropy is kbln q plus del E by T. Okay. Can you argue this how this can be derived or can be understood? This understandable? Why it should be?
Which one? This formula.
This formula, entropy formula. Why this is kbln q plus E average by T or internal energy by
Yes,
T?
I have problem in the last part. Average by T. Why it's adding in that?
Yes. So this derivation is not very much straightforward. Let me give some idea. Okay. Now you know the partition function. This is not related to this question. This is different. Let me different box. Okay. So there are two terms called work and heat. Okay. Do you know this work and heat? You
Yes.
know how you know that d cross q or du from classical thermodynamics. It is d cross q
DQ plus D
plus
cross
d
W.
cross w. This is our change in internal energy. So how you can write it? This means this you can write. Okay.
Yes.
Now you know that what is the main original form of that average of internal energy, that is EJ PJ. If you consider the canonical ensemble, this is probably any average. For any average, this is the general form. You know, for any average, if it is X, then also it will be XJ PJ. Here it is internal energy, so
Yes.
it will be EJ PJ. This is not the molecule. Again, I'm saying this is not the molecular average. That means this EJ are not the molecular energy levels. No, that was epsilon J. That is different. That is for molecular partition function. This is the canonical ensemble. Means you know, in the last class I did that canonical ensemble part. Here, that's why I'm writing this. This is the canonical ensemble, right? So here there are several energy levels. So these energy levels for each microstate, the energy are not the same. So there may be some energy, some levels with energy capital E0 or capital E1, some energy with capital E1, some E2. These are the energy levels. These are not as such levels, energy levels, not due to rotation or vibration, not like that. These are energy levels of the microstates. In case of canonical ensemble, these so it is epsilon j pj. Now, so what will be d epsilon de? So there are two variables, so you can write it d of epsilon j pj, not epsilon ej pj. So it is essentially pretty straightforward. Or let me write it. Is it clear?
Yes.
Yes. So this first term is basically represents the del Q. That means the heat, and it is the what?
How?
How? That's $1 million question. This is just an argument. Till now, scientists are trying to find out the best definition for this heat and what. But here we can argue. Let's say there are some energy levels. These are that energy
No, no,
level of
I'm
the, ask,
I'm asking about that is the summation EJ DPJ. This is
huh?
for D cross Q. Exactly. This is not for D cross W.
No, the first one is for D cross Q.
Okay, that's what I'm saying.
So how you can think that, let me say, let's say there are some, these are the energy levels. So when you change, when you give some heat, del Q, this is due to the heat, right? When you change the heat, what will happen is this energy level will be altered. The energy level will not be altered. Energy level will be same.
No,
E0, E1, E2. The energy of the levels will be
molecules will
same.
be
Not molecules, the microstate, number of microstate.
population.
Population of the microstate will be changed. Some population, just you think now this picture, let me copy paste this. It will be very, it's not difficult. Okay, so let me do it. So there are infinite number of copies, right? Microstate. These copies are called microstate that we have discussed. Let's say, let's say there are a1 number of copies, just a1 number of copies, number of microstate with the energy e1, a2 number of microstate with the energy e2, a3 number of microstate with the energy e3, like this. So in general, you can write ai number of copies in the ej number of microstate or copies with the energy ej, and it goes up to infinity. So how you can write the energy levels? Energy levels will be e1, e2, e3, e4, e5, and so on, infinity, up to infinity. And ground state there are a1 number of copies, just I have drawing this a2 here, a3 here, a4 here, and so on. So you can write, so total, what will be the total energy? Total energy will be epsilon j, aj, ej, sum over j. This should be the total
Summation.
energy. This should be the total energy, capital E.
Yes,
Okay. And what? And this will be the total number of copies. And that is essentially,
yes.
that should tends to infinity. That should tends to infinity. So these two are the restrictions. This is very much similar. So this is the, and now if you calculate the E average, what is the E average? Same, EJ and PJ. PJ is the probability. So probability, how you can write? Probability is just, can be written like this.
Yes,
This is the probability. So you can write it EJ AJ divided by this capital A. So just this is the our internal energy, average of internal energy. And after from these I will do it in the next question, or the some later question, that how you can calculate the partition function from this quantity, this average. Okay, so here this is now if you change, let's say if you give some heat, if you give some heat in this system, what will happen? Obviously, heat you are giving, that means overall energy will increase. Overall energy will increase
yes.
means, overall energy will increase means energy levels are not changing. That means some energy, this some
Population is going upward.
population means some copy, some microstate will be with some higher energies. Let's say this is now a minus 5, this is a plus 2, this is a 3, like this. In this way it will change. So that means this population is changing. So that's why it represent the del Q. And when you are giving some work, let's say for you are compressing the system, then what will happen? For each copies, there is only one original macro state. You are making the copies. So for each cases, when you are suppressing the piston, that means the volume of that macro state is decreasing. Then what will happen? For each copies, the volume will change. And that's why the what will happen? The energy level will be changed, in particle in box or in particle in 3D box. That is strictly depend on the volume. When the volume is changed, You can do it. For particle in box, the energy is n squared h squared by 8
n
ml
square h
squared.
square upon 8m square.
So from here you can calculate the daily. Daily means the energy levels, energy gap between two successive energy levels. That is n plus 1 minus n. So what will be this? N plus 1 square minus h square divided by 8 ml square minus n square h square by 8 ml square, right? So if you increase the length, if you increase the length, what will be the answer? N plus 1 square minus n square into h square divided by 8 ml square, like this. So from here you can see, if you increase the length, daily will decrease. So energy level will be more
Yes.
dense. So energy level will be more dense. That means the energy level, this is changing. The population is not changing. So that's why this represent the B cross Q. Okay. So in this way you can understand this, why this is D cross Q,
Wow.
why this is D cross W. Okay. Uh, so this is
Easily
clear.
got understood. Yes. Thank you.
Okay. Now the molecular interpretation, if you look at, so molecular viewpoint, okay. So you can write it D cross Q. So what is a D cross Q? EJ DPJ. Okay.
Yes.
So if it is, and uh, let me do it. Okay. From here you can do, but one thing I have to introduce. Introduce 1 minute. Let me check. Can I do it by skipping this part or not? So you can write it in general, D cross Q, just from this equation. From this equation, you can write it daily average minus sum over J, PJ, DEJ. You can write it. Okay. Is it clear?
Okay. Yes.
Okay. So, if it is, then what will be beta? Mm, So you can write it. If you multiply it by beta, what will be the changes? If it is beta d cross q, then it is beta, yes, minus beta pj dj. Okay, is it clear?
Okay.
Now from thermodynamics, what you know, that TDS, then beta d cross q will be ds by kb.
Yes.
So you can write it here. So it is actually ds by kb equals to, okay.
Okay.
So this part can be written as epsilon plus 1 minute. It is q. Okay, q will be there. So I have to insert the q. How I can insert? For that I have to introduce this f function. Otherwise, it is very difficult to do. Okay, let me think. Or I can do it the next class, because the if you I have follow the standard procedure now, I have to introduce a function f, which is like df. Okay, let me introduce. Otherwise, it can't be this f. F is let's say ln q. Okay, if f is ln q, it is clear. F is ln q.
What?
I am
Okay. Okay.
defining I am defining just a function. Q, q is the partition function, and I am defining f just another function which is ln q. Obviously, it will be
Okay.
ln e to the power minus beta ej. Nothing is there. I have just defined. So if you do, then you can check it by yourself. It's nothing there. You can, if you differentiate, then df will be e average.
dq by q.
That will be, but if you do it properly, you will obtain this. Okay, you will obtain this.
Yes. Okay.
How you can obtain this? Just you make the differentiate with respect to the beta and ej, then I will give it, I will upload it, okay, or I can solve it, but it can be done. It is not very difficult. It is just doing a numerical solution, just like we have calculated the internal energy average or other things in this way. You can do it.
Okay. I will do it.
If you can't, I will do it in the next class. This step is, you can think like homework. It's not very difficult. So if it is clear, if you agree with it, then it is easy. You can write it beta daily plus daily beta. It is just I have added. Okay,
Okay.
this, so now this essentially means when you do it, then obviously these three terms will be there. First df, then beta will be there, e average, and then e and average of d beta. So these three terms will be there. So it is beta this is there. Okay. So this part, if
Okay.
you can try it, otherwise I will do it the next day. It is not difficult. It is just a doing two-page calculation. Otherwise. So just this lesson we needed this lesson. Now you can, this part is this part directly. So you can put it.
Yes.
So you can write directly comparing. So what will be ds by kb will be d of f plus beta d average, or ds is equal to this. Now you just do integration. So S will be KB F plus beta E. It's okay. One thing should be
Why there
there.
is not kb on that?
So KB will be there. So it will be KB beta. KB beta means,
1 by
okay.
t.
And C will be there. C is our integration constant.
Yes. Is it important?
It is important, but we will take C will be 0. Why? C should not be 0 or may not be 0. C may be 0, may not be 0. But if you think in our thermodynamics, we always consider del S, right? So in both cases,
Yes.
when you consider, then the C will be same. CF minus CI. C
Yes.
may not be
It
0,
will be
then
0.
C will cancel. So for simplicity, we consider C as a 0. So if C is 0, then, and what was the F? F was ln Q.
Yes.
Okay. So this is the formula for entropy.
Okay. Okay.
So just we have to derive this part. Okay. You try, otherwise I will do it the next steps. It is not difficult.
Okay, sir.
So now we have, now what was the question that I have to calculate the S for distinguishable and indistinguishable. So if it is distinguishable, then Q will be Q to the power n.
Q to the
And
power n.
this E average we have already calculated, right?
Yes.
What was that?
4 at t.
So let me, okay. So 4 RT divided by T. Okay. So S will be KB and it is ln q, that is n ln q. So it is kb n ln q, and q was given as a to the power 4, plus it is just for r. Okay, and
Okay.
kbn will be r, because here n is actually the na.
Yes.
So in general, you can write, if you take r common, then it will be 4 plus ln a t to the power 4. This is considering the distinguishable part in particle, and if it is indistinguishable, then it will be kb. Just changes will be that q, right? So now let me write, q will be q to the power n by n factorial. Essentially, it means that ln q is n ln q minus n ln n plus n.
Plus n.
So this is q. So now we have to calculate the s, that is kb ln q. So kb n ln q minus kb n ln n plus kb n, and then plus 4r. Just instead of kbn, I have replaced this as r. So it is r ln, what is q? Q is a t to the power 4 minus r ln n, and it is plus 5r.
High bar.
This is the answer. Okay. So it will be s for indistinguishable. Now, what will be the indistinguishable factor? We have defined that already. I, for s, it is s considering our indistinguishable, considering distinguishable. So it will be r ln a t to the power 4 minus r ln n plus 5r divided by r ln a to the power 4 plus 4r. R will be cancelled out. So ln a to the power 4 minus ln n plus 5 divided by ln t to the power plus 4. It's okay.
Okay.
So again, you can simplify. Mm, So it, oh, on this, let me complete. Okay. So it can be written as by n. N is actually Na, right? Na.
Yes.
For this is for all 1 mole plus 5 divided by ln a to the power 4 plus 4. So like this. So again, you can simplify it. But the original answer will be this. Okay. So because how we can simplify this? This 5 can be written as ln e to the power 5, and this can be written as ln e to the power 4. So essentially, it can be written as ln a t to the power 4 e to the power 5 by n divided
Minus
by,
82.
no, why minus? Ln a by ln b
Ln
is
A by
not,
ln B.
it's not related. Ln a by b, it's
Okay.
ln a minus ln b. but it's ln, so like this. So it is the answer. Okay.
Okay.
Okay. So okay, in this context, I can discuss your question that Helmholtz free energy and also the Gibbs free energy
In the next question.
in the next question. This question has been done. It was a very long discussion for the first question. Okay, so before that, I should I discuss the pressure part?
Okay.
Okay. So let me calculate the pressure, then Helmholtz free energy, and Gibbs free energy calculation for canonical ensemble. Okay. Let me drink some water. Pressure. So for in general, we know that if you calculate any property x, how you can calculate that xj, pj.
PJ.
Yes, and you know that pj is e to the power minus beta
P.
ej divided by partition function.
Yes.
So you can write it xj e to the power minus beta ej divided by q. And the definition of q is the partition function, which is sum over beta ej. One thing you have to keep in mind always, here the summation over the states, not the levels. If you consider the level, then you have to consider the degeneracy. Okay, so this is our now for pressure first. The P average, it is small p and it is capital P. This is for probability. So for small p, it will be always same Pj, capital Pj, and you know the form of, okay. What is the Pj, how you can write it? It's p power minus beta ej. Okay, you can write it. So now, one thing it is needed here. Otherwise, you can't do it. That's why here you know the form of the E average. E average we have already discussed before. Yes, this is the form of E average. Okay, is it clear? This is the form
Okay.
of E average. Okay, so if this is the form of E average, then what will be the
PJ is PI by P.
Pj? Pj will be
AJ by A or anything. NJ by N.
no, no. It's not that much easy. You have to calculate the expression for Pj, the pressure. Then you can do. So how you can do it? Easy. is- I have to look for the, yes, from here you can do it. If it is zero, here is Pj, right? So from here you can do. Let me check if there any another option to find it out. Okay, okay, okay. How you can write it? Just follow it. Dej. Okay, Dej can be written as minus Pj into dV. Is it clear?
Okay.
How? Let's say you are doing a work done. You are doing a work done. Okay. So when you are doing a work done, then essentially the energy levels are changing as we have already discussed. Correct. So if the
Okay.
energy levels are changing, that means that will be dEj, and it should be the Pj into dV. We have to need a understand this very carefully. We have to need a definition of pressure for each energy levels. How we can do it? We know the EJ. For in case of calculating it is easier for calculating average energy because it was EJ PJ. This EJ, this EJ was the our energy for any jth level. But here you need the pressure for any jth level. How you can calculate any pressure for any jth level? This is not very much easy. So you have to understand this physically. So when you are doing some work done, already we have discussed here we have discussed these two terms appear in case when you are doing some work done, or you giving some q, it will change the internal energy. This is the due to internal energy, and this is due to our work done part. There are two parts. So here we have to consider that this work done, due to that work done, it will be dEj, and it must be equals to minus Pd, which is this is just like d cross q is equals to minus Pdv.
PDV.
This is just like this, nothing.
Okay.
Okay. And this d cross q is dEj, already we have discussed.
Yes.
So now if you from here you can write the Pj, it is minus del Ej del V at constant volume, because you are taking derivative with respect at constant number volume, so number should be fixed, because you know that Ej was function of A, N, V, and E. Okay, so 3 was there. Also temperature is also. So this is the definition of uh, Pj. So just you can write. So now P average will be sum over minus del Ej by del V constant volume, number and temperature both are there, and Pj, capital Pj is e to the power minus beta Ej divided by Q. Okay, it's clear.
Okay.
So you can write it as like this. No problem, I think
Okay.
you can do. So now
Yes.
now you have to play a trick here. So Q is sum over J e to the power minus beta Ej. So if you calculate del Q del V, then what will be sum over J del V of e to the power minus beta Ej, where it is a
Vitamin.
function of NVT. Correct?
Yes.
Okay, so what is constant here? Beta is constant. So because
Yes.
temperature is constant, so beta will be here. So it is del V of. So you are taking so it will be, you can write it Ej
To the minus beta is.
NVT into del Ej del V.
Yes.
Okay. So what was our numerator? Minus beta Ej del VNT, it will be minus beta Ej. So it can be written as del Q del V divided by NT divided by beta Q. Hence, the pressure P average will be not sum over 1 by beta Q del V N T. So essentially you can write it as 1 by beta dln q del v nt. Okay.
Yes.
And 1 by beta is,
KBT.
so this is the form of average pressure. Next, Helmholtz free energy. Here only one trick was there, not trick, this knowledge is required. Otherwise, rest part is easy. This DJ. Helmholtz free energy. How you can calculate Helmholtz free energy? You know, Helmholtz free energy is A. How A was defined? U minus
U minus TS.
Ts. So average of A can be written as
Summation
average.
AJP.
No, these things are not needed. Now you can do it straightforward. You know the E average, you know the S average.
Yes.
Just put it. Now this distinguishable, indistinguishable, this part will come if you consider the molecular partition function. Otherwise, it's correct. So in case of E, what will be the what is the E average? Value of E average? KB T square, then D ln Q.
Del LNQ by
What
D.
del N Q del T at constant NV. And what was this entropy part? KB ln Q, KB T ln Q. No, KB ln Q. KB or KBT? KB or KBT? What was the form? KB ln Q.
KB.
KB ln Q. KB ln Q minus KBT del ln Q del T NP. So what will be the answer? Okay.
Okay.
So for canonical ensemble, the Helmholtz free energy is directly related with the partition function. You can see KBT, you know, this is just beta, this is constant. That's just ln Q. That's why that function I am talking, right? This function F, this function is actually the Helmholtz free energy with some constant. You can see
LNQ.
ln Q. Helmholtz free energy is also ln Q, right? ln
Yes.
Q. Minus KBT is a constant part.
Yes.
So that's why that Helmholtz free energy is
Temperature
called.
is also constant.
Temperature is also constant means you are not uh, when you are considering a system, you are considering the ensemble, canonical ensemble, the temperature is constant, no? That's why NVT for canonical ensemble.
Yes.
So for canonical ensemble, NVT is constant.
Okay.
So that's why this Helmholtz free energy is called Helmholtz free energy is uh, direct thermodynamic analog of analog for canonical partition function.
Directly related to Q.
Yes, that's right.
What mean by analog?
Analog means the represent. You can say just like
LNQ.
no, Q and A are the same quantity. I want to mean analog means actually here
Okay.
like that. Analog as you have received probably here. Now another part is gives you energy or why should enthalpy? Enthalpy. Enthalpy. These are all straightforward right now. What is the definition for enthalpy? H equals to
U plus PV.
U plus PV.
Del U plus P delta V.
Volume is constant, so this will be there. You know. U average, this is essentially the E average, which is KBT square B del L N Q. I thought I will discuss this part in the next class, but okay. Del T NV plus V. What is the P average? This part. Let me copy. No, this is easy. KBT DLNQ del P. KBT del LNQ del V at constant
Delphi.
N. Okay, so you can write E equals to KBT common. It will be T KBT V. Okay,
Okay.
so this is enthalpy, and another one is Gibbs free energy. How you can do it? G equals to
H minus Ts.
exactly. So H is this part. This is our H. And what is the S? Ts, right? So it is minus T, and S is KB ln cube
And then Q.
plus KBP del ln cube.
Del T.
So this term will cancel.
Yes.
So left part is, you can take KBT common, then it will be just V dln cube del VNP minus ln cube.
Ln Q.
So this is our Gibbs image. Okay. Okay.
Okay.
Probably this will be calculated in the class as well. I don't know.
This week I think not this is calculated.
In next week probably it will be calculated. Okay. Yeah.
May I know one thing?
Huh.
Sorry for this question. What is A in the Helmholtz function?
What is the
A.
this A? This A.
Yes.
That
Yes.
is a representation of Helmholtz energy. A notation for enthalpy it is H.
Okay.
Ga is the Helmholtz energy.
This was not at the chemical thermodynamics, I think.
No, no, it is there. It is there. It is standard notation. Okay.
Okay.
5 Okay, this is very important question. I was in doubt whether I should do it now, but let me do it. Calculate the um, fluctuation of internal energy or anything. It will be same, but mm, it's better. Okay. Calculate the fluctuation and relative fluctuation both.
What is fluctuation?
I will explain. For internal energy under canonical measurement. So, this is from statistics. Okay, you have to understand what does it mean the fluctuation. One thing you will hear in future that the statistical mechanics is all about average and fluctuation. Average and fluctuation. Average we have studied, right? This E average,
Yes.
S average, H average. These all are average quantities. Means because you are doing the statistical mechanics, you have lots of molecules, and that's why you have to take average for any quantity. Let's say E, you are taking this average and you are saying that this average should be equals to our classical chemical quantity, thermodynamic quantity U, right? Internal energy. But that's why you have to taking average, because there are lots of molecules. That's why this is the statistical mechanics, statistical thermodynamics. The statistics is there. That's why we are taking average. How we are taking average? That sum over J, EJ, PJ. This is the statistical
EJ,
distribution.
PJ.
This and this is under the ensemble average, considering the ensemble. If you have to consider the time average, I have also I've thought that for time average you have to consider that E, and that is changing with time dt divided by tau in this way. But that is difficult to calculate. That's why gave us a bypass theory of ensemble. By using that ensemble average, you can do it. So this is our average. Now forget about this thermodynamics. Consider any quantity, any number. Let's say I am giving you 10 number, any 10 number, that is n, any 10 number, 0, 1, 5, 7, 3, 2, 11, 25, 6, 8, 19, 13. So what will be the average of this 10 number? How you can calculate? Just you have to call,
Adding and dividing by 10.
yes. Essentially you are doing nj pj, correct?
Yes.
You are doing this, but here for all cases, this pj is number of 1 by 10
1 by
for all
10.
cases, for all cases. That's why you can do it by 1 by 10 and adding the all nj's. So it will be
Yes.
0 plus 1 plus 5. What will be this? 6, 13, 13, 30, 30, 55, 55, and 20, 74, 13, 80, 7 by 10. Okay, so give it to a round figure. Let it 5, or it is 4, and it is 2. So it will be 90 by 10 now. So it is 9. So this is the average value. Okay, is
Okay.
it clear?
Yes.
Is it clear? How we have calculated this average? Doing this. Okay. But now calculate after calculating average, you have to calculate the standard deviation. Do you have studied standard deviation?
Yes.
Yes. What does it mean? Standard deviation means now if you plot, this is very crucial. Let's say here if you plot, the numbers are, where is the numbers? One is here 0, one is 1, 5, 7, 4, 12, something there. But there is an average value which is 9. But
Yes.
there, if you look at, there is no number, 9 is not there in the list. In the list there is no 9. So 9 is the average value, but for each value, there is a deviation from the mean value. This is called average value or mean value. Okay.
Yes.
What does what first we have to calculate the variance. How we calculate the variance? Variance is actually the deviation from the mean value. that is called the variance. Okay.
Okay.
Okay. Variance is actually calculated as, just look at it. It's easy. Its variance is actually the, for each number, for 0, what will be the variance?
9.
9. For 1, what will be the variance? 8. For 2, not 2. For 5, what will be the variance? 4. So for each cases, you can write down the variance. It will be 9, 8, 4, 2, 6, 5, -3, -13, then it is -10, -4. Okay,
Okay.
is it clear?
Clear.
So what does the definition of variance? Variance is actually the average value, um, minus original value that we have. Okay,
Okay.
this is the variance. Now just add it. What I'm saying, just understand. This is the, just let me write variance for j, that is, as it is easy, just this is our variance. This was capital N, not the small n. Okay, this is average value minus nj. That's why I have written here the variances. Okay, now if you have to average the variance, you have averaged the number. Now you have to average the variance. How you can average the variance? How you can average the variance?
Taking average of all the variance.
All the distribution. Now I
Yes.
say, what is the standard deviation? Standard deviation is same, just it is the square of variances. Nothing is there, just square. This is the standard deviation. Okay,
Okay.
for each term j. Just write the standard deviation. What will it be? For first case, what is the standard deviation? Say it.
0.
No, standard deviation,
Sorry, 81.
81. Then 64. So you can calculate it, right? So it will be positive for all
Yeah.
cases. So this is the standard deviation. Now, not square. Now, if you have to calculate original standard deviation, you have to just average it. So how you can do it? So it is, let's say, sigma j, it is sigma j square. So it is essentially mj square. Okay, it is difficult, I think. Uh-huh. Just look at, this is the sigma j square, this part. And if you take the average of sigma j square, what should it be? Just I put the, instead of sigma j square, I put this value. Is it difficult?
No.
Okay. It should not be. It's just a mathematical part. It was in class 12, I guess. It is in mathematics.
Yes.
So just you open this, so it will be n square minus, this is the nj square plus nj square, I guess. Yes, plus nj square minus 2n nj. So first term is this, next nj square average minus 2n nj average. So 2 times average does not mean anything. Average of average is just average. Nothing is
Average.
there. This is nj average, nj square average, nj square average, and this is 2n n. Okay, is it clear?
Okay. Yes.
Because average of 2 is 2, average of n is n average is n, because this is okay. Let me write one intermediate step. This will be this, and this will be this. So directly you can write again average of average does not mean anything, and average of nj. Average of nj, you know what does it mean? Average of nj.
Yes.
Average of nj means n average that we have already calculated. So essentially it means this. Okay. So it is n square average minus n average square. Okay. Is clear?
Okay. Yes.
So this is the formula for our standard deviation. So what this standard deviation says, that how much the original values is deviating from the mean value, right?
Yes.
That's why it's essentially signify the fluctuation. Fluctuation means the deviation from the mean value,
Standard deviation.
standard deviation from the mean value, sigma square. Sigma is standard
Okay.
deviation, sigma squared is the fluctuation. So sigma will be just root over this, the same thing.
Yes.
So this essentially signifies the fluctuation. You can understand from the term fluctuation how much is fluctuating from the mean value, original values are. So it is important. Let's say if you have a sample set where you can see here the fluctuation is huge. If you calculate the fluctuation here, it will be huge. It's varying from 0 to 25. So fluctuation is huge. So when the fluctuation is huge, then uh, considering the mean value is not suitable. Is it understandable? Here the value is varying from 0 to 25. Let's say you have 10 people with the this values considered the age. 0, 1, 5, 7, these are the age. So it is not considered the value, the average value for these 10 people of age is 9 years. This is not correct because this fluctuation is huge, right? When the fluctuation is less, then you can calculate, then you can consider. Fluctuation is important. When the fluctuation is big, very much, then considering the average value is meaningless. So that fluctuation we have to calculate. Here we are calculating the average values only. Everything we are calculating in terms of E average or S average or H average. Let's say you calculate the E average value is 10, but when you calculate the fluctuation, it varies 100. Fluctuation 100. That means your internal energy value is 10. You have the value you are considering the internal energy is 10. Also, the original value of the molecule is varying from minus 90 to 110. So that is not acceptable. So that's why the fluctuation is important. If the fluctuation is used,
Okay.
then average value is meaningless. That's why you have to calculate the fluctuation here. So we have to calculate the fluctuation for internal energy. So how we can calculate this? Sigma E square, just same. It is E square average minus E average square. E average we have already calculated. What was the value of E average? E
4
average.
K 4 RT.
No. That is for some example in general. It is in general.
Summation EJ PJ.
For
Okay.
canonical
Please
ensemble we
family.
are doing now. This is our E average. Here we have to calculate first the E square average. Then just we have to subtract that. So what is the E square average? You know, for any average, it may be anything. Here it is E square. It is EJ square, EJ.
Square J PJ.
Is EJ square, not E square, EJ square. Term is EJ square. So how you can calculate this EJ square PJ? PJ is Q. So we can write it
Yes.
1 by Q. Okay.
Okay.
And now you know that Q, not Q. Let's say you are defining a term, uh, gamma, any gamma. I'm just defining. ej e to the power minus beta ej. If it is the gamma, then what will be del gamma del beta constant of NV. What will be this?
My minus ej e to the power minus beta ej.
Minus
Ej first on the exponential, it will come in the
ej
front, and
square.
after that same.
Ej square will be there. 1
Yes,
ej
ej
equals
into
to.
ej square.
Okay. So I can write it.
Okay.
So it can be written as 1 by q del beta of gamma. And gamma is sum over ej beta ej.
Yes.
Clear?
Okay.
So you can write it 1 by q del beta divided by q into q. No problem. Just I divided by q and it multiplied by q. So what it be? E average into q. Is it clear?
Okay.
Hmm. So now we have to just take the derivative. First, E average will come out and it will be del q del beta constant of NV plus then q will come out and it is del E del beta constant NV. So minus the first term will be E average 1 by q dq beta. So it can be written as, just look at it, minus 1 by q
ln
dq.
q.
Yes, so it is dln q del beta NV. And the second term will be just minus,
Cancel out q and 1 by
yes,
q.
NV. Okay.
Okay.
And this part, this minus dln q del beta is E average.
Yes.
We have already did that. And the second part will be remaining there.
Del E average. Del beta.
So it is just E average square.
Yes.
So E square average equals to this. So directly you can calculate E square average minus E average square is minus del E average by del beta NP. Okay. Now put
This is
1
the
by,
standard deviation.
yes, but still we can simplify it. Just put kbt instead of beta. So it will be kb t square
Square del
dt
E del T at NV constant.
nv. What is this? Cv.
CV. Yes.
Okay. So this is the our
Okay.
this is or cvm if you consider for 1 mole of gas, then it is cvm. Okay. So now in there it should be written as cv. So it is our sigma e square. This is our standard deviation for canonical ensemble.
This is the fluctuation.
If you take the root over it, then it is the standard deviation.
Okay.
Fluctuation of internal energy under canonical ensemble. But what I have argued that we have to check whether this value is big or not, whether this is a very big with respect to our average value. So that is important. That is the relative fluctuation that we have to calculate. Then only we can comment on the validation of the average values. So relative fluctuation is important. Relative fluctuation, you know, that is sigma E bar. So it is sigma E square divided by E average. Just I have divided with by the average value. This is the fluctuation and this is the average value. So essentially it will guide us the relative values, right? That's why it is relative fluctuation.
Yes.
So you can calculate. So it will be kb t square cv. Okay, and the E average is kb t square. What is kb t square? Kb t square dl and qd. So let me write it
DL and
just
QDT.
d average, E average. Now how we can calculate it? We have to now calculate. Let's consider a monoatomic gas, monoatomic ideal gas. You know. So for monoatomic ideal gas, what is the daily? What is the E average?
3
3
by
by
2
2,
KT.
3 by 2 R T. For this is 1 mole. Okay. You are saying the molecular partition, molecular average. This for canonical, Na will be multiplied and it will be RT. Okay. So what will be the CV?
Okay. 3 by 2 R.
3 by 2 R. So just write it. So it will be KB T square. It will be, okay, one thing, square will be there. Because if you square it, then obviously it will be very big. You should not square it, the sigma in. Okay. So it will be kbt square, then 3 by 2 r to the power half divided by E average. What is E average? 3 by 2 RT. So it is kb into 3r by 2 to the power half divided by 3r by 2. Okay.
Okay.
So it will be kb divided by root over
3R by 2.
3r by 2.
Total
Okay.
root over.
So actually, one thing we have to keep in mind that this is for, if it is for 1 mole, obviously. So then if it is for 1 mole, then obviously here also you have to consider the Na term. Then R will come out. Okay. Here you can see this
Okay.
KB is there. KB is there means this is not for 1 mole. If it is for 1 mole, this then obviously the N term will be there. So for that, it's better to, instead of R, we should, it is KB. So it's okay. So it is better to deal with KB.
Okay.
Okay. Is it clear?
Clear.
Okay. So what is the value? If you calculate it, what will be the value? It will be 2
Under root 2
kb
KB
by
by 3.
3. So now if you calculate it, what, it's very small value. You know the value of kb.
Yes.
So you can ignore 2 by 3 even. So it is around 10 to the power minus 23 by 2. So it's around 10 to the power 12, minus 12.
Minus 12.
So it's very small value. So that means the fluctuation is very small. So you can see the average value is E average, and the fluctuation around this average value is very small, 10 to the power minus 12 relative fluctuation. So if say it is 10, so the original values may be 10 plus 10 to the power minus 12, 10 plus 3 into 10 to the power minus 12. So fluctuation is very small. Okay. So that's why
Okay.
we can do, we can deal with the canonical ensemble because here the fluctuation is very small. Okay. So we can do it.
So it is not important, the fluctuation.
Fluctuation, no, fluctuation says that we can deal with the average value. So fluctuation is, it should be, the fluctuation is should be very less. So let me do it uh,
It
by
is very
different.
small.
Yes, it's very, very small. So what should I do here? Instead of KB, it should be written as N into KB, right? Instead of R, because you
Yes,
don't know it is whether it is 1 mole or not. So it's better to deal with KB into D. Okay. So it's better. You can do with R. That is not problematic. But R means it is for only 1 mole. But it may not be 1 mole.
yes,
So that's why it's better to do it KB into Na. So in case of KB into Na, here will be Na term. This Na term will be N term will be there. Okay, so if N term will be there, then it will be KB will be cancelled out because KB square and half will be there. So KB square will be cancelled out. It will be 3n by 2 root over 3n by 2 divided by 3n by 2. Okay, so it is actually uh, 1 by root over 3n by 2. So that means it is around n to the power minus half. That's already we have did. Again, we know the n. So you can see here why I use this, change it from KB to n, because now you see if n is very less number of molecules, then this fluctuation may matter. Okay, do you get
yes,
it? If let's say n is 10, then the fluctuation will be around 10 to the power minus half, means 1 by root over 10, or instead of 10, 9. So it will be now 1 by 3, so it is 0.33. And let's say your average value is 2, then it's matter, right? Then it
yes.
matters. But same thing, if it is 10 to the power 23 for 1 mole of gas, then obviously you can think it is negligible.
It doesn't matter.
So the validation of average value is always depends on the fluctuation. This is 10 to the power minus half. So this value is very small for any macroscopic system, you can understand. So what does it mean? That a typical macroscopic system, the relative deviation from the average value, that is this standard deviation, the fluctuation into the power minus half, is very small. That means the probability distribution of energy is narrowly fit. Means what does it mean? That if a function is like this, it is the average value,
Yes,
and this deviation essentially signifies that fluctuation sigma.
yes,
Statistically, it was the value, no? If you plot that 0 1, you get this. But here the fluctuation is very less, so it will be like this. Get it?
yes.
This is 0,
Got
and this is a what kind of function? Delta function. I said it.
delta function.
This
Yes,
type of function is called not Dirac delta function totally. Dirac give the idea of this function. So essentially, this Dirac delta type of nature should be important in case of statistical mechanics. If it is the reverse one, then you can't do with the average value. Then average value does not make sense anymore. So that's okay. So let me stop here today. If you have any doubt, you can ask. So it's
okay,
today's class is quite uh, high higher in sense. It's difficult, I think. Some more rigorous discussion we have done today. Okay. So anybody, if you have any doubt, you can ask me.
I have got one doubt.
Yes, yes.
Yeah, regarding this assignment for week 5, question number 8,
1 minute. Week 5, right?
unit 5, question number 8. For the expression of pressure in terms of canonical partition function for 1 mole of an ideal gas at 300 Kelvin in terms of gas constant R is, means what parameter we have to find here?
Uh, Let me check. Question number 8. Form the expression of pressure in terms of canonical partition function. Yes, for 1 mole of gas. Okay. For 1 mole of an ideal gas in terms of gas constant. Pressure you have to find. Okay, average pressure.
Average pressure. Okay.
Yes, this average pressure. This average pressure you have to find. Just
Thank
look, the temperature is given.
you.
Okay, 1 mole means Na will be multiplied here, so it is Na kb. Na kb is essentially R, so R is also
Mhm.
given. So everything is given.
Mhm.
Just you have to calculate that. Okay,
Okay.
so
Thank you.
okay, so now if anyone does not have any question, I can stop sharing first. Okay,
Thank you.
okay. So again, we'll meet next week from 4 p.m. So now you can leave and thank you for attending.